So now that we've seen this calculus of variation stuff, let's actually start applying that to classical mechanics. So again, the reason that we're doing this is because Newtonian physics deals with the fact that we need to know all the forces and we need to generate the accelerations in any general type of coordinate system, which for the most part could be literally almost impossible to do that. Now, also, we have constraint equations that need to be added to some systems. For example, if we had, I don't know, like a bead sliding down some sort of curved rod or something like that, some curved wire, again, just simply writing the constraint equations, it's going to be nearly impossible to actually do that. So we want to come up with then a different way, which then allows us then to circumvent these issues to basically work with every coordinate system we want to work in, which allow us then to ultimately come up with Newton's laws. Now, what this means is we're going to come up with a new way, which uses all this calculus and variation stuff that we've basically been talking about, which is more general than what it is in Newtonian physics. It's actually easier to solve, which actually makes it more fundamental. And as I mentioned before, it's actually the basis of pretty much all modern physics that we know of today. Also, if you're going to do things like thermodynamics, pretty much this is the basis of thermodynamics as well if you're talking about non-equilibrium type situations. Now, it turns out that nature pretty much always wants to minimize something. So whether that's energy or free energy or whatever, nature always wants to find a way to minimize some particular type of quantity. So this is what this principle or this new way of actually doing physics is based off of. So based on the idea that basically something in nature always wants to be minimized, which then allows us to then determine what is the path at which this object is going to follow. So this brings us to what's known as Hamilton's principle. So Hamilton's principle basically states that what? Of all the paths along which a dynamical system may move from one point to another point. So let's say basically I have something like this, where I have one point here, I have another point here, and out of all of these paths, which this thing can actually follow, going from the one point to the other point, given the fact that the constraints are met, right, so I have some constraints along here, let's use yellow as well. So out of all these paths that this thing can follow in the same amount of time of delta t, consistent again with all of our constraints, the actual path followed is the path which minimizes the time integral of the difference between the kinetic and the potential energies, which is what's known as the action. So basically what this says is we're going to define this new quantity, which is known as the action, which is then equal to the integral over time, so from the initial time to the final time, of then the kinetic energy minus then the potential energy. This is what's called the action. So what Hamilton's principle says is that the path that the particle follows, whether it's this path, this path, this path, or this path, within this constraint of time, so it has to be from that same initial time to final time. So this is my initial time, this is my final time. Oops. I messed that a little bit. There we go. My final time. And let's say this is the initial position, let's call that x1, to the final position of x final. So how this thing goes from here to here in this amount of time of delta t is given by the path which minimizes this particular quantity, which is what's known as the action. Okay. So in terms of calculus of variations, what that means then is that the variation of the action, which is then equal to the variation of the integral from the initial time to the final time of dt of t minus u, must then be equal to 0. Okay. So again, all this states is that this thing has to be an extremum of it. It has to extremize this path in a particular way. So again, an extremization means it could be the minimum or it could be the maximum. It doesn't put any restrictions on which one it is, but as long as it extremizes this particular integral, then this is going to be the path that the particle is going to follow when going from point A to point B, or from point 1 to point 2, or the initial point to the final point, however it is that we want to state it. Now, typically, what we know is that what the kinetic energy in a generalized coordinate system, or at least in a Cartesian coordinate system, is simply going to depend on the velocity. Right? So this thing is going to depend on the first derivative then of the position, and then we're going to sum that over all the I directions. And then the potential, again, as long as this thing goes with a conservative force, then this thing is usually going to be a function of only position. Right? So this is only going to depend on position. Right? Now, as we talked about before, when we talked about energy, this thing can depend on time as well. So if I had a system which was, say, losing energy to something, so it was radiating energy away, this thing's going to be time dependent. And in some situations, it turns out that this thing can also be velocity dependent. So for example, whenever you have a magnetic field, you also have a vector potential. And that vector potential shows up then with a velocity term associated with it. So it turns out that this thing can actually depend on both velocity, position, and time, but for now let's just pretend it depends on time. So that means if we plug these back in here, then this thing is going to be equal to the variation then the integral from the initial time to the final time, dt then of the kinetic energy, which depends only on the first derivative, the potential, do it this way, minus then the potential, which again depends on this guy and possibly time, so I'm going to put that time in there as well. Now this quantity of t minus u, this thing we usually give a special name. This is what's known as the Lagrangian. I'm going to write it this way. So L is what's known as t minus u. So some textbooks you'll see this is usually given as either a regular L or curly L, such as the one that I drew here. Typically when you're talking about classical mechanics, the distinction doesn't matter. It doesn't matter if I have curly L or capital L. They basically mean the same thing. If I'm talking about something like quantum field theory, they do have drastically different meanings. Typically, if you're going to see a regular L, say something like this, this is what you would call the Lagrangian. And then when you see a curly L like this one, that's what's called the Lagrange density. So it's actually the Lagrangian per unit volume. So in that case here, you'd be integrating over 4-dimensional space as opposed to just 1-dimensional space. So you'd be integrating over the volume and the time when you see something like this. But again, that distinction is pretty much only used in something like quantum field theory, not necessarily in something like classical mechanics. Again, classical mechanics, these two things are the same. It just depends on how the author wants to write it, or how the book or the paper wants to display that. So let's go back to here. So again, what this means then is that this is equal to then the integral from the initial time to then the final time of the time then of the Lagrange, what's known as the Lagrangian, which depends then on the position, the velocity, and then in general on the time. Right? So this means that all we're going to do then is vary this particular object, which is what's known as the action. Okay. Now, if we map that over to what we were doing before, so again, if we talk about the calculus of variations, so there what we're doing is we are varying our integral j, which was then equal to the variation of the integral from the initial position to, say, the final position, dx then of f, which depended on y dot, and in general on t. Then we can identify these two things as the same, because again, what we wanted to do here was set this variation equal to 0, which is what we want to do here as well. So basically, following what we did with calculus of variations, as long as we make certain identifications, we can then easily extract what we did in calculus of variations now to this new quantity, which is known as the action, or in this case, f is what's known as the Lagrangian. So here, as long as we make the identification that x from here, sorry, this was x, not t. There we go. So here, x then goes to t when it comes to the Lagrangian. Y goes to xi, and y dot I goes to x dot I. So as long as we make these identifications, be between these two quantities, now we can carry over exactly what we did from calculus of variations now to classical mechanics, and in this case into the action. So what do I mean? So what I mean is, so here, what we saw was that this gave them the Euler equations, which then said that what? The partial derivative of f with respect to y minus then the derivative with respect to x, and then the partial of f with respect to y dot, then was equal to 0. So again, here, as long as I make the identification here, and also that f goes to the new quantity of L, known as the Lagrangian, then here we can then say that we have the partial derivative of the Lagrangian with respect to xi minus then the time derivative of the partial derivative of the Lagrangian with respect to x dot I must then be equal to 0. So in terms of classical mechanics, this is now our new Euler equation, which is actually what's known as the Euler-Lagrange equation. This is known as the Euler-Lagrange equation because we're working now with classical mechanics instead of just any type of system. So anytime this thing is applied to classical mechanics, again here the integram gets identified then as the Lagrangian, which again is the difference between the kinetic energy and the potential energy. And then this thing is what's known as the Euler-Lagrange equations instead of just the Euler equations. So basically, this Euler-Lagrange equation is then gives you what's known as the, again, Lagrange equations of motion. So by solving this system, we then get the Lagrange equations of motion. So let's apply this to a physical system to see if we get the right answer. So again, the claim is, and we're going to discuss why this is actually true, that even though we're using this new thing, this abstract thing, which is the difference between the kinetic energy and the potential energy, or overall this integral, which is the action, this whole thing then, using the Euler-Lagrange equation, should give us actually Newton's second law. Okay, this is how this thing is going to work, and we'll talk about why this actually makes sense in just a second. So, our example, let's do a quick example. Let's look at a simple spring mass system. Right? So again, let's say I have a spring mass system where this thing has a spring constant K, this has a mass of M. Let's say, again, this thing is displaced from equilibrium by an amount of X. Let's say it has some sort of velocity. Doesn't matter which direction it's going. I'm going to say it's moving in this direction. Okay. So from here we know the kinetic energy is then simply equal to 1/2 m times x dot squared. Right? We know the potential energy is then equal to 1/2 kx squared, right? Just the spring potential energy. So this means our Lagrangian then is going to be equal to the kinetic energy minus the potential energy, which is then simply going to be 1/2 m times x dot squared minus 1/2 k times x squared. So basically now what we want to do is apply the Euler-Lagrange equation and make sure that indeed this thing actually gives us Newton's second law. Okay. Now just remind ourselves, Newton's second law, you know we've seen this 100 times. We know that the sum of the forces is equal to m times what? X double dot in this case. Right. So in this case the only force which is acting on it is the spring force. So I get minus k times x is equal to mx double dot, which means 0 then is equal to mx double dot plus k times x. So let's apply our Lagrange equations. So here I'm going to get, let's look at first the partial with respect to x. Well here that's going to give me simply what? Minus 1/2, actually 1/2 is going to go away, so this gives me minus k times x. And if we look at the partial of f with respect to x dot, then that's going to begin m times x dot. Talk about what some of these quantities are in a minute. So now if I apply the Euler equation, this gives me the partial of L, partial of x, minus d dt, of then partial of f with respect to x dot must be equal to 0. So here then I get a minus k times x minus the derivative of m times x dot is equal to 0. But as long as the mass is constant, then this is going to be mx double dot. And then I can multiply through by the negative sign. So finally what I get is mx double dot plus k times x is n equal to 0. So indeed, these two give me exactly the same thing. So good. So why does this work? And why is this something which is reasonable to expect that it works? So let's talk about that. So again, let's go back to the Euler's equation. So I'm going to write this as 0 then is equal to, again, the partial of the Lagrangian with respect to xi minus then the time derivative of the partial of Lagrangian with respect to x dot I. Right? Now again, just to remind ourselves, again, in general, we're going to call t here equal to only a function of x dot. And then we're going to say u is then in general going to be a function simply of xi. Now, again, there are cases where at least this statement is not true, right? Where this can depend on x dot and can depend on t. Again, a particular situation of that is what's called, well, not called, but would be electromagnetic, for example. This term here is usually what's known as the generalized momentum. Reason for that is, as we just saw in that last problem, if we took the partial of L with respect to x dot, we got simply m times x, which is the momentum. Now, this is what's known as the generalized momentum or the canonical momentum, because it's not always just m times x dot. Okay? There are times, again, going back to electricity and magnetism, since the potential is going to depend on x dot as well, so when you take the partial of the Lagrangian with respect to x dot, make that dot a little bit bigger, what will happen then is you get the usual m times x, but you also get another term from here, which means that you end up with a modified momentum, which has the usual momentum, which is what's known as the kinetic momentum, plus some extra term, which is what gives you a different momentum, which is known as the canonical or the generalized momentum. Now, if you're doing something like quantum mechanics, it turns out that it's the generalized momentum or the canonical momentum, which is the term which doesn't commute then with the position. So typically, when you would have, what was it, x and p, so I did x and p equal to I times h bar. This p then is the canonical p, also known, again, as the generalized momentum, which is not necessarily the kinetic momentum. So typically, you have to be a little bit careful working in whatever system that you're working with. So again, if your potential here does have a term which is velocity dependent, i.e. this thing does depend on x dot, in that case, this is not going to be usual kinetic momentum. It's going to be kinetic momentum plus something else, but it's only that total momentum which gives you the Heisenberg uncertainty principle. So not just any type of momentum. Now, again, all that was a little bit outside of what we're actually talking about, but just know that that term is actually what's known as the generalized momentum. So good. So let's go back. So let's put these in here. So this is going to be now the partial with respect to xi of then the kinetic energy minus the potential energy minus ddt of the partial with respect to x dot of then the kinetic minus the potential. So here, what's going to happen then is that since this only depends on x dot, the partial derivative of that will go to 0, so I'm only left with him. So this is going to be equal to minus the partial of the potential with respect to xi. And then here, again, typically the velocity term, or the potential is not going to depend on velocity, so this term is going to go away. So this is going to be minus ddt of then the partial derivative of the kinetic energy with respect to xi. So from here, this is actually the same thing as minus the gradient of the potential. But we know minus the gradient of potential is simply the force. So this term then is going to be simply equal to the conservative force. And then here I get minus the derivative of this guy. But again, the kinetic energy is simply going to be the generalized momentum, or just simply the momentum. So this is a minus ddt of simply the momentum, which is simply Newton's second law. So from this would then give us that the force then is equal to the derivative of the momentum with respect to time, but this is simply the second law. Okay. So basically, the reason that this actually works and the reason that this actually makes sense is, again, under usual type of circumstances where this thing is only position dependent and this thing is only time dependent, or not time dependent, but velocity dependent, this whole entire structure, again, leads to the fact that what? We end up with Newton's second law. But again, we're going about it in a different way. So here, the only things we need to know are the kinetic energy and the potential energy. We never need to know what are all the forces, which is what this F is, and also what is the momentum or the acceleration. Right? We don't need to know those things. And here, again, the potential energy and the kinetic energy are both scalar quantities, which means nothing in here is actually a vector, but everything in this expression is actually a vector. So when I first write this out, when I take this derivative, this is technically only the ith component in the ith component. So this is the ith component equal to the ith component. But again, what this does is it basically gives me what? Using scalars, it then gives me a vectorial expression, at least the components of a vector. So from the scalar quantities, I actually am going to get a vector, i.e. I'm going to get Newton's second law out of it. Now, of course, by now you might be thinking to yourself, well, you know, why bother if this thing only gives me Newton's second law anyways? Well, again, the nice thing about here is, again, this thing, first of all, has nothing to do with vectors, so I don't have to know what the forces are. I don't have to know what the accelerations are. I don't have to worry about working in a particular coordinate system where I can actually write those things down. I can actually choose whatever coordinate system I want to, and this is going to pop out every time. Also, it's a lot easier for me, based off what we talked about last chapter, again, using all of our constraints, how to actually put in constraints into all this to see where this is actually going to go, as opposed to, again, working with Newton's second law, working with forces and trying to write those constraint forces, which, again, may actually be impossible to actually do. So